So today we're going to talk about statistical significance, and last week we talked about clinical relevance. We'll just make sure we understand the distinction between the two. I have some keywords for you to know. Make sure you know the meanings of all those by the end of the day. So what do we mean by statistical significance?
When you analyze the data, statistically the p-value is less than 0.05. So, but clinically it could be or it could not.
Right, you were very good at that last week, saying it's significant but not big enough to matter. So what is a p-value? What does it represent?
The occurrence of a particular condition, occurrence or the chances of it occurring.
So if it's a small p-value, you have a very small chance of anything working?
No, larger chances of what?
Because there isn't a significant difference between the comparison values that are taken.
So how can a p-value be little if it represents the difference? The bigger the...
I think it's the ratio. I don't remember more than that.
The p-value is a very confusing and unknown concept. And over the course of classes that you have with me, we are going to make sure you know what it means. And you have the basic understanding that you exhibited last week, so half the job is done. If somebody asks you what a p-value is or makes a statement that something was important because the p-value was small, I want you to be able to discuss with them and educate them on what it really means. So as part of being a master's student, you will review papers. And in the conclusions, if they say this was important because we had a really tiny p-value, you will say, no, that's not why your conclusion is important. So we're going to talk about what does statistical significance mean. In order to do that, we have to talk about a null hypothesis. So what's the null hypothesis?
It's the converse of what you're trying to prove.
I would not say that that is correct. In a way, it's related. But first of all, you said trying to prove. That is a biased statement. So we don't want to say that. We want to go in and say, does this matter? And so in that context, what's the null hypothesis?
It doesn't matter.
It doesn't matter. Or null means zero, none, no difference. Null hypothesis, no difference. A statistical test tests the null. And this is a thing we got to remember. We're not the alternative, or the true difference is not what we are testing. We are not determining if there is a true difference. We are determining if the null hypothesis is true. So getting a p-value of any value gives you no information about the alternative. We're going to see why that is in a second. So the other thing that we have to, well, here's on this slide, I'll just mention a few things. So there's meanings of the difference between groups is not greater than would be expected by chance. I like to say that what we do first is see if we can rule out chance as a reasonable alternative. So rejecting the null hypothesis is basically ruling out chance as a reasonable alternative. It doesn't say how big the difference is, just that we have ruled out that this finding is not likely to be by chance. And I think so along with that, you can only reject the null hypothesis, say it's unlikely, a small p-value, unlikely. Or if you get a big p-value greater than 0.05, you fail to reject the null hypothesis. You do not prove the null. You cannot prove the null because you don't know where the other distribution is. So it's kind of like if you think about our blood pressure example where we had a distribution, if your blood or your IOP, if your IOP is greater than 22, it's unlikely that you have a normal IOP. But if it is 18, that does not mean you are normal. Okay? So you can't say you're normal. You just can only say you have abnormally high IOP with respect to that distribution. So it doesn't say how important it is, how big that difference is, anything else. It just says you're not normal. Now, so our p-value. I think one of the things that you have, statistics is all about managing variance. And if you flip a coin and it's a fair coin and you flip it 100 times, you're not likely to get 50 heads. I mean, you have a better chance of getting 50 heads than any other number, but it's not very likely you're going to get 50 heads. It's not 50% of the time you're going to get 50 heads. It's only like 14% or something.
That's the chance, right?
That's the chance. And that chance has a spread. If you flip a coin, a fair coin, 100 times, you can get a value of 0 to 100 heads. Now, 0 and 100 isn't very likely, but it is possible. So we have to think in terms of we're going out and we're sampling, and a sample isn't the truth. A sample is a sample, and if you sampled many, many times, the average of, if you sampled an infinite number of times, and you averaged all those samples, that would be the truth. That would be the real underlying mean. Now in statistics, we don't know what we don't know. We don't know the alternative. We don't know the truth. I have this joke I always tell, but you guys won't get it because you probably haven't seen the movie. But there's this famous movie, A Few Good Men, about this guy. These guys on the witness stand, and he's kind of a bad guy, and Tom Cruise is grilling him, and he says, I want the truth. And the guy says, you can't handle the truth. And so it's not that you can't handle the truth. It's just not that you'll ever know it. But one thing as statisticians we do know. We do know what the distribution should look like if there's no difference. So if the null is true, we know mathematically what the distribution is. Given a certain standard deviation, our means, or we look at the means, and those means will come up with a distribution. And in fact, the distribution that we are interested in is the distribution of the test statistic. So, t equals the mean of one group minus the mean of another group over these are standard deviation, the variance. Actually, I should have said SD. That's actually a z-test. We want SD. So you square the standard deviation, divide by n, add those two, take the square roots, and that's the pooled standard error. And this difference divided by the pooled standard error is a t. Now when we talk about a distribution around the null hypothesis, we're talking about the distribution of this t value. We're not looking at differences between means, we're not looking at means, we're looking at the distribution of the t. And if the truth is 0, if the real truth is 0, we will have a distribution around that 0 just by chance. This is, if you get a 1, that the truth is 0, but the t value can be a 1 by chance. It can be a -1. It can be a -100. It can be anything by chance. But the distribution looks like this. And most of the values are 0, but it's not very frequently that it's 0. So when you find it, when you do a test and the two means don't exactly match, equals 0, the question is, how different are they? Are they different enough to fall out here and be beyond 5%? Now, an interesting thing is we do a two-tailed test. So 2.5% is on this side, 2.5% is on that side. So when we say less than 5%, it's actually less than 2.5% of this tail, 2.5% of the other. There are one-tailed tests, but they're not either.
T here is the truth.
T is a t-test.
T-test, yeah.
Yeah.
And that's
the statistic.
For determining the
To determine if two means are different.
If two means are different.
Yeah, and there's other kinds of tests. There's binomial tests. We have the coin flip example, and what's the probability of finding, if the coin, if we're testing a fair coin, the null hypothesis that we're trying to test is probability of 0.5 getting heads. But you're going to get some number other than that. And it's going to follow a distribution like this. So if the coin is fair, it's going to be mostly 0.5. But it could be the probability of the actual data that you get might be that 40% of the coin flips were heads. And how far away from, or how far out on this tail do we go with the number we get? So if we saw 100 flips and we had 3 heads, that's pretty unlikely. We would say our coin probably isn't fair. The probability isn't 50%. But it could be. It's not that this is 0 chance. It's just a small chance. But what I want you to understand is that this distribution is the distribution of potential t values. So this probability that you get out here, so if you found it right at the line, you would say that p value is the probability of finding this test statistic t when the null hypothesis is truly 0. It doesn't say anything about your current experiment. It doesn't say what the difference is. It's only looking at what's the probability that you would find this result when the null hypothesis, the hypothetical null hypothesis, is true. So you're not testing an alternative, you're testing the null. And so the p-value is the probability of finding a test statistic as great or greater than the p-value that you get. That's why it says p less than, if the null hypothesis was true. So the null hypothesis isn't necessarily true, but if it was true, this is the probability of finding that t. Does everybody get that?
That's why p is a small number.
That's why p is a small number. Because the smaller it is, the less likely the null hypothesis is true. And so you reject the null hypothesis. But again, you do that without any information about whether the difference is clinically important. And that's how we had that really small, I think it was like 0.002 or 4 or something last week on PALs and SBLs. It was a really small p-value. The likelihood of the null hypothesis being true was very small. But yet, the difference wasn't enough to bother with from a clinical point of view. And all tests, all studies have to be read with that in mind, because people give you p-values, they don't give you effect sizes. And so you as clinicians have to make the decision, is this difference important to me? And you don't get that information from the p-value. So in one thing, the bigger this difference, the smaller the p-value. How else can that p-value be small? If this is the formula. What else could you change? Let's say God decides these numbers. God decides the variance out of the sample. You have no control over that. Well, you have a little bit of control over the variance depending on how cleanly you do your study. But generally speaking, you try to keep the variance as small as possible and create your conditions and remove bias and stuff like that as best you can. Randomize, for example. But what can you control in this formula? What can you control as an experimenter? Look at that formula. What in there do you control?
Sample size?
The sample size. And so what happens to t as you change this number?
Inversely proportional. So
yeah,
t value increases if you decrease the sample size. Or increase the sample size, decrease the t value.
The other way. Your t gets bigger. Your p gets smaller.
P gets smaller, yeah.
The t gets bigger. So, so the t is this scale down here. And so as t goes 2, 3, 4, 5, 6, the p is going down. The probability of being under that distribution gets smaller. So if the people last week of the PALs and SBLs, they had like 240 subjects. If they only had 40 subjects in each group, the P would have been like 0.2 or 3. So it was 0.002 because they had 240 subjects in each group. So you have to be careful with that. If you see a study that has a big sample and they find significance, then that's why you see studies, epidemiological studies, and they have thousands of people in them, and then they talk about the significance of these various little elements. It's very common in nutrition studies. So like vitamin E was statistically significant when we had, thousands of people. Well, the p-value is pretty meaningless in that situation because everything is going to be significant when you have thousands of people. And so you have to look at something else when you're looking at that.
So is this why population-based studies are not as good as...
No, they're fine, because what happens when you increase the sample size? What's a good thing about increasing the sample size?
Bias is less?
No, not necessarily. The bias, if there's bias, it's going to be there no matter how big your sample is. But the accuracy, your standard error, your confidence interval gets smaller as the sample size increases. But that was Fisher's. The thing about bias is Fisher's complaint about. He said that R.A. Fisher is the guy who, if you've heard of analysis of variance, and there's an F test. The F stands for Fisher, or from Fisher, and he was a very famous statistician in the early 1900s. And he didn't believe smoking caused cancer. And people would do this epidemiological study after study, because you can't randomly assign people to be smokers. So you can't do a randomized controlled trial. So his argument was that he felt there was a gene that was controlling both the need to smoke and cancer, and that it didn't have anything to do with smoking itself. And so his argument was, well, you've shown this relationship, but if you have the same bias, it doesn't matter how many studies you do, the same bias is going to show the same result. So he kept rejecting it. So the key here is the p-value represents the probability of finding a particular statistical value, a t-test in this case, given. It's that area under the curve, this probability of being a particular value or even smaller than that, with the stipulation that the null hypothesis is true. So it's not that your difference is true or that there is some difference. It's that the null hypothesis is true, 0. So I think the p-value is important for ruling out chance, but it's only important for ruling out chance. It's not telling you how big the difference is. I have a coin flip table here, and this is just kind of an example. Like if you have, if the probability is 0.5, if the actual coin is fair and it's 0.5, then the probability of getting 35 heads out of I guess this is out of 80. To get 35, 40 would be 50%. 35 is 0.05, 0.048. So that's a one-tailed. I guess I do have 25 is 0.025. That would be the two-tailed test. 25 or 75. We don't see those table cut off, but 25 or 75 would have the same probability, 0.026. And adding those together would be a 0.05. So the probability of getting 25 heads or less or 75 heads or more is less than 5%. In this case, even if you were at half, half is the most frequent one. You can see the numbers go up and then go down, but you only have a 0.089 chance of getting 50% heads when the truth is 50%. So, 1 out of almost, not quite even 1 out of 10 times you're going to get 40 heads. And then if you go down to 40%, which would be 40% of 8032, I don't show that one. How about 0.3? Oh, that's hard to figure out. 0.2. Anyway, you can see that kind of the probabilities there. This isn't a table to memorize or anything, just kind of showing you how it works. Yeah, if we were going to ask amongst you, I didn't do this, but if you were going to flip a coin, then would you call heads or tails? And a lot of people maybe pick heads. Some people pick tails, but there's a preference, and it's usually a bias towards one or the other. We can't really know if you have a bias. We only know if you would. We could not confirm a bias. We could only test if you rejected. If you said heads, if it was 50% and you said heads 80% of the time, we would say you're likely biased in calling heads as opposed to tails. But we don't really know where your bias is. We just can reject that it's not, that it's not no bias. I don't know if that was helpful or not, but the p-value only reflects whether the test statistic is an outlier for the null distribution. And so we've said that enough times. Okay, now this is kind of, I say hypothesis testing is a two-stage process. Actually, I think it's a three-stage process, but the first two stages are, first, you determine if chance is a reasonable value, and that's the t-test. And that's what we just talked about. And then we determine if the non-chance, if you do reject the null hypothesis, is the non-chance different clinically relevant, and that's effect size. And you guys have all done effect size calculations now. And notice the similarity between these two equations. They both have a difference between means, but this is the pooled standard error that sums the two standard errors, basically. And this takes the average standard deviation. So the difference here is in terms of standard deviation units, and the difference here is in terms of standard error units. And remember that standard errors reflect this hypothetical variance. Its standard error is not something that you calculate. It's an estimate of a hypothetical distribution of means. There's not a real distribution of means. You can't measure it. It's an infinite distribution, infinitely large sample. It's the population, and it's a hypothetical number. We know the standard error from simulations and formulas and solving the equations and everything else, that the standard deviation divided by n and divided by the square root of n is a good estimate of this hypothetical distribution. And so the t is in standard error units, the effect size, these hypothetical standard error units, and effect size is in terms of the actual standard deviation, the average standard deviation for your two groups. Does anybody have any questions about this? The third stage is you replicate your results, because remember, this is just a sample. It's not going to be the truth. And if you replicate, you get a little bit closer to the truth. And you take the average of the two means. If you do it a third time, you get even a little bit closer. So you think of when you take blood pressure, you usually take it more than once, or you can take it more than once. And then you average those, because the average is closer to what the true blood pressure is. Well, when you replicate a study, you're finding you're getting closer to what the true difference is. And it's really important, if you find a therapy that works, it's kind of unusual that nobody's thought of it before. So if you see a publication where they've published something and they say this works, well, you want to replicate it to make sure that it really is the truth. It's not, because it's surprising that they found something better than standard. And so you want to make sure that's the case by replicating. So hypothesis testing is really a three-stage process. Eliminate chance, test effect size, replicate.
So you're talking about repeating the test, but did they do that for everything?
No.
I mean, you're wasting time, right? Somebody has already done the study. And
See, you're thinking that of wasting time. And I would say no. If you look at the Travatan and all those blood pressure drops, there's a lot of studies doing basically the same thing and getting a distribution. Again, it kind of depends on what you're testing as to whether it should be replicated, and usually replicated by somebody in a different lab too. It's important because you don't expect to find something better than the standard of care. And when you do, you're all excited. But there could be something underlying that, and somebody else should show that. I mean, a few years back, somebody demonstrated cold fusion, which is, I don't even know exactly what that is, but it's this energy source of from being able to harness the sun type energy, but without blowing up everything. And then, so they wrote a paper and it got published and it was all nice. Nobody could replicate it. So it didn't really happen. It was very surprising. And so people tried to replicate it and they couldn't. So it wasn't really true. And there's a lot. If you listen to the bad medicine tapes, you'll see that that coming up, that you need to replicate, especially when things are surprising. What time is it? Wow, I'm done already? Oh, no, I'm not done. Okay, so the question is, summary of the semester. Does the evidence support using a particular intervention? So the first thing we do when we want to figure out what to do for a patient is we do PICO, that's our literature search. We search on the population that we're, say, glaucoma, the intervention, say, drops, the comparison. We want to study one eye drop against another. The outcome, does the IOP go down? We want to assess bias. It's a randomized controlled trial. We can be more confident that we have controlled for bias. But even in that context, you need to look and see if, one thing you need to do is, now you have randomly put people into different groups, but look at the control group. What is the alternative? Is it realistic? Would you prescribe this control medicine to a patient? Or is it an artificial kind of thing? Is the dose too low? Or do they measure things too fast? So if you did a restasis study and you look to see if anybody had done any better in a week, well, you wouldn't find restasis did any good because restasis takes 3 months. So you have to kind of, even though you randomly put people into restasis versus vitamin A, if you look after a week, you're not going to find any difference. And in fact, restasis or vitamin A might do better because it can react faster. But you haven't been fair to restasis. So it's supposed to act in 3 months, so in 3 months you test it. But then also, if you just find, you look up people that had restasis, and you go into your records and you say, okay, we prescribed this person restasis. We prescribed this person to drink water or something. And then 3 months later, you find out that the water people are better. The restasis people still have dry eye. Well, you don't say restasis isn't as good as water, because why? Why, if you went into your medical records and you looked at people that were taking restasis and you measured their dry eye at baseline and at 3 months, and they maybe got a little better, and then you looked at people who came in with dry eye and you said, well, drink more water, and 3 months later they had either gotten a little bit better, let's say they also got the same better, would you say that restasis is no better than water? Can you conclude that? Why not?
The effects are the same.
But
the effect.
Symptoms wise, we don't know what decreased what. I mean, it's very it's qualitative rather than quantitative. So.
Well, you use your tear film breakup time, so it's pretty quantitative. You find that this one group, their tear breakup time was a little bit longer, and they're both about a little bit longer, about the same. So are the two groups, so is restasis the same as drinking water?
Would be easier in water, and subjects would probably be drinking water over restasis.
Yeah, money wise.
Money wise it's better. but have you shown that water's the same, as effective as restasis? You go in your records, you want to study the effect of restasis. So you find people who've taken it. And then you found people that have dry eye that haven't taken restasis. And so you know that your standard procedure with people with dry eye is to tell them to drink more water. I don't know if that's really true or not, but let's just say it is. And so you have the water group versus the restasis group, and they both improve, and they both got a little bit of improvement. So there's no difference between your standard of care and water suggestion and giving them restasis. Is there no difference between the two groups? Do you think there's a difference between the two groups? Yes or no? Who says yes, there's no difference? Or let's say, who says you have proven that proven's a tough word. There's no difference between the two groups. Who says that? Now, come on, you got to commit. You're doctors. You're making a decision. Do you choose, you have a patient, you say, well, normally I would give this person restasis, but I'm not going to do it because of my study in my records. How many would choose not to do restasis because of your study? You did this study, you found no difference, you're going to say, I'm not going to bother with restasis. It's not worth it.
But will this be pretty similar?
I'm not convinced though. I mean, because I don't know why, so I'm not convinced. But yeah, if my evidence base says no,
Yes.
Then I won't.
But your point?
This could be pretty similar to this being statistically evident but not clinically significant. Majority, we may see people not preferring this.
Well, in terms of clinical relevance, you haven't shown any difference. There's no clinical significance. There's no statistical or clinical significance because there's just no difference. All right. So you're having trouble means that we have to make a very important point. This was not a randomized study. Okay? One group you prescribed restasis. The other group you did not. Why do you think you did that?
But we give them water, which is like a placebo.
It depends. Some people believe in water, some people don't.
So cannot declare because it is affecting.
I mean, if that person comes in, they have dry eye, and you just say, well, here, try this water. Or you should drink more water.
But they don't know that it's water. Why do you tell them?
No, you're not. You're looking in your records. You're not saying here's a jar of water. You're saying you note in your notes that you told this person to drink more water, and they did or didn't, but the next time their dry eye wasn't as bad, and you gave people restasis, and you're assuming that they took the restasis, and after 3 months their dry eye was a little bit better too, but not different than the people that you said water to. So the problem is your sample is probably biased in what way?
Choosing.
No, you prescribed. They weren't choosing. You said, or you recommended.
We created the bias.
Is what?
We created the bias. So we instead of randomly giving that this person is going to get water and this person.
Well, you're in a clinical practice. Hopefully you don't randomize people into stuff. You say, okay, this person, their dry eye is such that our only option now is restasis. Whereas the other person, you say, well, let's try water. So you have two people, one group, the water group, their dry eye either isn't as bad or you haven't followed them as long as the restasis group. You told them maybe water in the past and nothing happened. So now you're giving them restasis. And so you're comparing somebody who doesn't have a very big problem to somebody who does have a big problem. And the person that doesn't have a very big problem, some little thing like water, might push them over the edge. And somebody that needs restasis also gets restasis, and it does a little bit of help. So by not randomizing, you have a bias in your samples. Now, most studies in optometry that you read about are not random trials. They are in things like drops and restasis or something like that. But in many conditions, a person has a condition and you believe something will work and you give it to a bunch of them, and then you look where they are here and then where they are later, and you say, oh, okay, they got better. And maybe you look at people that you didn't do this treatment to, and they didn't get better. So you then see a difference, so you believe your method works. But you don't know, they didn't necessarily start in the same place. So you can have people who start dry eye, group 1, the stasis group. This is their baseline. And then the next time you measure them, a little better. And so this, that difference, this difference is the same as that difference, but you know, it's not like it didn't have an effect. You're comparing apples and oranges, and so that's why this bias thing is a big deal. And so you have to be careful with that. So assess bias. The other thing you want to do is you want to select papers where the subjects match the profile of your patient. So if you have a 60-year-old woman in your chair, you don't want to match them to a study done on optometry students. Then you look to see if the results were significant or not. You want to eliminate chance. And then if you do eliminate chance, then you look to see what is the expected benefit. What's your effect size? Did we? Oh, I was thinking I had already done this. Okay, so in our paper that you read, did you calculate effect sizes yet in your homework?
No.
Oh, man, I was thinking you did. Oh, I spent too much time on that. Okay. So when we look at this paper, we notice that the age is plus or minus, or the mean age was 41 plus or minus 10. So the appropriate age is like 20 to 60, 21 to 61. Both sexes were included. The tear breakup was 3.5. So it was between 0.5 to 6.5 seconds and so forth. Now, yes, we did. We did with the Travitan study. So I want you to make sure you know how to, all this stuff over here is what we get out of a demographics table. When you read a results section, usually at the very beginning they describe their population, and that's where you want to match. Then you look to see if there was the same thing. So in this case, let's go on to the next slide. These were the results. They show their figures. Notice that the error bars, these are means plus or minus standard errors. Remember that non-overlapping standard errors do not necessarily mean that they're significantly different. Here is something let's look at. Let's just review this. Now that chance has been ruled out, you proceed to clinical relevance. You have the baseline of restasis, vitamin A, and control. I'm not a fan of restasis. My wife, Cher, has dry eye, and Dr. Dahl said you need to take restasis. Restasis is $1,000 for every, I don't know, I don't think that's a month. I think it's for 3 months. But for the rest of your life, It's not like you can ever stop. I'm going to be very poor when I stop working. How am I going to give her that? So I want to look for alternatives. Now, vitamin A drops, they actually looked a little better here. Now, I looked up to see where to get vitamin A drops. You can't get them in the United States. So even though they did as well as Restasis, we can't get them. And in this case, they gave them to the person 4 times a day. I think they both burned, but does Restasis burn? We never got it, so I'm not sure. I know IOP drops burn, but I don't know if these burn or not. Anyway, when we look at this, we see that the cyclosporin, which is the Restasis, versus vitamin A, the difference was 0.83, the effect size was 0.49. In other words, we have essentially a minimally clinically relevant improvement of vitamin A over Restasis. I mean, it would be good if they were the same, because both of them are way better than the control. But the fact that vitamin A is even better is a suggestion that we should work on vitamin A drops, and maybe. So that's just looking at this. Now, I don't think the authors conclude, I don't remember what they conclude. Maybe they conclude that Restasis really helps, which it does. But vitamin A is better. And cheaper. Yeah. Yeah, a lot cheaper.
But oral vitamin A wouldn't work as much.
See, my question is, do you think a vitamin A rich salad with omega-3 dressing could work as well? I mean, that's what I would try. I would see if that works. Now, my wife does not like fish. I can't get her. So she's just going to keep crying for the rest of her life when she walks outside. So, fine. But we did increase our salad, and I tried to get, you can get omega-3, kind of a fish oil lemon kind, to use as salad dressing. It isn't going to happen. So anyway, that's where we are. But I would think it would be much better to have a salad every day with omega-3 salad dressing than spending $1,000, $4,000 a year on a drug. I mean, think what you can do with $4,000. So, anyhow, that's where I am. So, does anybody have any questions?
Actually,
yes.
This is actually not from this topic. I think I forgot a few things. We were discussing about confounders in the previous chapter.
Yes.
So I was reading up a few studies where they were adjusting the confounders to get a desired result, or to get a result that they want, kind of a thing.
Yes.
So aren't we doing a bias there? Like, we're trying to remove the factors that is influencing them.
Yes.
To get the result that we want.
So
what are we trying to prove there?
So there was
I'll give you an example.
Okay, good.
First study. So they're trying to understand the prevalence of myopia.
Yes.
Across the world, basically. And one of the things is whether playing outside would reduce playing out in the sun.
Yes.
Playing
right. Protective outdoors. Protective. Yeah.
Would reduce myopia, or cause a decrease in the axial length. So in that, they adjusted some of the confounding factors, and they found that after adjusting for confounders, there was a significant negative association between myopia and outdoor activity. And adjusting for the same confounders for each hour increase in outdoor activity, there was a hyperopic shift and decreased axial length.
So what were the confounders?
They didn't mention what the confounders were. No. They just said after adjusting for confounders. No.
So the so let's look at what a confound. Let's distinguish between and I'm going to tell you this is a problem in the literature because there is a difference between a confounder and a mediator. And you want to adjust for confounders, but you don't want to adjust for mediators. So, well, let me do the smoking one. I can't think for myopia an example. Although, if maybe we can come up with something. So we have outdoor activity leading to axial length. Now, a confounder is something that makes a person go outside and something that is related to axial length. We can use near work. Okay.
Near work is one of the causes.
So if you do a lot of near work, what happens to outside?
The physical activities reduce.
Yeah, you're not outside. You're inside.
Yeah.
Okay?
Yeah.
So near work causes outdoor activity. Near work, you got this stuff up here, you're accommodating, you're doing all kinds of stuff, you're causing blur. So that's going to cause axial length. Now, I don't believe they adjusted for near work, but if they had adjusted for near work, so the question is, let's look at people who do a lot of near work, a little near work, and then of those people, how many are outside a lot? Outside a lot or a little. And so now, if we find axial length is shorter here under both these conditions, then you've adjusted and taken out this confounder. So you're controlling for near work if after you look at people who go out, they do a lot of near work, but somehow they find a lot of time to go outside too.
Yeah.
So you have those two conditions. People that do a little near work, some of them go outside and others just, I don't know, sit around and stare at themselves or something inside. And so there's a little, but it's the same. And then we can see if there is an effect of axial length. Now, a mediator is in this direction. And so, did we talk about the paper where they looked to see if statins led to AMD?
AMD, yeah.
Okay, so we have taking statins, and then let's see, actually, if you take a lot of statins, then you probably have high lipids, and then AMD. Now, if you adjust for lipids,
Smoking and alcohol.
well, just adjusting for you, I don't know, actually this would work a whole lot better if it went in this direction, but that's not what they tested. So, if the question is, does lipids affect the AMD? Well, if you adjust for statin or not, then you're going to eliminate the effect of lipids, because you won't be taking lipids if you, or you won't have high lipids. But either way, adjusting this middle one just breaks this line, whereas adjusting for this one, you open up this test. In this case, you break it if it's dependent on this, then actually, I guess it would go this way. So these are the statins. If you, the whole idea is that lipids is A and B, but if you randomly or somehow control for this, you're going to wipe out the effect of the lipids. Anyhow, confounding versus mediation. So when you're doing your analysis, you got to be careful when you're controlling for stuff that you're not wiping out your effect. In confounder, you do control to see your effect. It's two different ways of looking at it. I have the slide, study your lecture, listen to your podcast, go over your quizzes, know how to compute these different things. Know your rules of thumb, less than 0.05, effect size greater than 0.5. And you need to understand the concepts, not just plugging numbers into formulas. And remember, in hypothesis testing, you never prove anything. In statistics, you don't prove stuff. You just, it's a fuzzy business. And you can